Hello, everyone. Welcome, welcome, welcome. Good to see you. Hope you had a great weekend and can't believe we just have 2 more weeks left and then we're actually finished with this class. Can you believe it? It seems like it's been forever and it seems like it went by so fast as well. So um, hopefully this is our last online class, at least mandatory online class that you'll ever take, and be back to normal in the fall. Everything's looking pretty good, right? So that's exciting. Um, let's see. There's a question here from Taylor that I think we'll start with. So Taylor, you want to ask your question?
Yeah, I just had a quick question with the positron emission and the electron capture,
Yeah,
because they do the same thing.
right.
Was it the positron that's more common or the electron capture that's more common?
The positron emission is a little more common, I think, but they're both fairly common. There's not a, I mean, and there's no way for us to be able to, from what we know, to predict which one of these two it will be. I'll give you a way to like predict if it's going to be beta plus or beta minus. So
Okay.
between an electron being given off or a positron, but electron capture between these two, it's not very easy to figure it out.
Okay.
Yeah.
Okay. All right. Thank you. That was all. That was all.
Yeah. Good. Um, is that right, Lewis? Is that what the new schedule says? I thought my classes were supposed to be face to face. I haven't seen it yet.
Yeah, it looks like they changed it. It was looking like it was going to be face to face, but the updated schedule as of today says mostly online with labs in person.
Really?
Yeah, so you might want to check it out.
Huh. Okay, I'll look at that. I hadn't heard that. Thanks for letting me know. I hope that's not the case. Okay, any other questions before we get going here? Our exam number 3 is going to be on Thursday, April 29th. It'll cover chapters 19, 20, and 21. And then the final is going to be on Monday, May 3rd, and it's going to be cumulative over the entire semester. Okay.
HR, do you know how many questions are going to be on the final?
I think it's about 50.
Okay, thank you.
It'll be about a 2-hour exam. Okay, any other questions?
When will the pre-test be available?
The pretest is already available.
Oh, okay, cool.
Yeah, yeah, should be able to take that. Okay, let's pick up where we left off last time. And so remember, we were looking at different kinds of radioactive decay. All right, alpha decay, remember, is the emission of an alpha particle, which is essentially a helium nucleus, 2 protons and 2 neutrons. Right. Beta decay is the emission of an electron. And remember, in beta decay, a neutron turns into a proton and gives off an electron. All right. The symbol for alpha decay is helium-2, 4. For a beta particle, it's electron -1, 0. All right. And remember, when you write these equations, that the sum of the mass numbers and the sum of the atomic numbers must be the same on both sides. And we'll do a few examples here in a minute. A gamma particle or gamma decay is really just when an excited nuclide gives off high energy light. All right. So for example, some of these other processes leave the nucleus in kind of an excited state where it has extra energy. And that extra energy is given off as a gamma particle. All right. So when a gamma particle is emitted, it doesn't change the mass number or the atomic number of the element. Okay. And then we have positron emission. Remember, a positron is like an electron, but it has a positive charge instead of a negative charge, but has the same mass of an electron. Okay. And that is +1, 0 E. All right. And there, instead of a neutron turning into a proton turns into a neutron. All right. And then lastly, you have electron capture, which achieves the same result as positron emission, but it does so by capturing an electron. And a proton, again, turns into a neutron with positron emission. All right. So let's just really quickly write some nuclear equations for each of these. All right. So alpha emission from uranium-238. You got uranium-238. To find the atomic number of uranium, you could look on the periodic table, right? And you find that it's 92. All right. And then since it's positron emission, we know it's going to be 2 for helium, right? And then to get the daughter, you just say, okay, what plus 2 makes 92, right? And you know that's 90. And what plus 4 makes 238, and that's 234. And then you go back to the periodic table and you find element 90, and you find that it's thorium. Okay, so that's positron emission. Beta emission, so let's say neon 24. Neon is atomic number 10, right? And beta emission, we know, is going to be a -1, 0 electron, right? So you predict the daughter again by saying, okay, what -1 gives you 10? And that would be 11. And the top doesn't change, so that's 24. Go to the periodic table, and that's sodium, right? Does that make sense? All right, then positron emission from nitrogen-13. Nitrogen-13, again, go to the periodic table, you find out that that's atomic number 7, right? And if it gives off a positron, that's +1, 0 E, right? Oh, you don't have to write that negative sign there. And then you say, okay, what +1 is going to give you 7? So you know that's number 6, right? The top doesn't change, right? So that leaves carbon, because carbon is element number 6. Yeah. And then lastly, electron capture by beryllium-7. So we have beryllium-7. Beryllium is atomic number 4, right? And if it captures one of its own electrons, the electron goes on the left-hand side here for electron capture, right? And then you do the same thing. This is going to be 3, 7 lithium. All right, does that make sense? So I'd like you to be able to write nuclear equations for each of those processes. All right. Okay. Good. Now let's see how we can tell what kind of radioactivity is going to happen. So far we know how to write these nuclear equations, but how do we know which one of these it's going to be? All right. Well, I'm not going to be able to show you definitively how to do that, because that would take more time and more in depth than we want to go into in general chemistry. But we can get some ideas. So really heavy elements. So it turns out that the stablest element on the periodic table. Oh gosh, I have a problem with my overheads here. Hang on for a second. Let's see, the periodic table. Yeah. The heaviest element that has stable isotopes, it's element number 83, bismuth. Okay, so everything above bismuth, and you can see in the periodic table that the atomic mass is in brackets, right? That's because those elements above bismuth don't have any stable isotopes, right? So they're all basically radioactively decaying, all right? And for those heavy elements, the one of the processes that happens quite often is alpha decay, which we talked about earlier. And you can see that if one of the problems of an element is up here, above bismuth, it's essentially too heavy, right? It has too many nuclear particles, and it has to sort of lose weight, if you will, right? And which process helps it to lose weight the most? Well, that would be alpha decay, right? Because you lose 2 protons and 2 neutrons, all right? So that's generally true for these very heavy elements. Now, for other elements and other radioactive types of decays, what we're going to look for as a guide, and again, it's not absolute, but as a guide, and oh, Lewis, thank you for sharing that. I was really worried that my classes were back online, and that would be bad news for me. So I'm glad my classes are listed in person. Shoo! Yeah, I requested that. I know they're thinking 40 to 50% of classes in person and maybe more, but I told them I want mine to be in person. I need them back. I need to be able to see you guys other than on my computer screen. All right. Sorry for the distraction, but thank you so much for telling me that, Louis. I was like, wow, don't tell me my classes are online again. I'm gonna die. All right. So one of the things that determines the stability of the nucleus is the relative amounts of neutrons and protons in the nucleus. Okay. So what do we know about protons? We know that protons are positively charged, right? And so, you know, why doesn't the nucleus just fly apart if it's composed of these positively charged particles? Well, there's another force that we really don't talk about in chemistry because it's called the nuclear force. And the nuclear force is what holds nuclei together, all right? But if you have too many protons without enough neutrons, the positive charges tend to repel each other without enough of the attractive nuclear charge. So one of the things that's super important in terms of determining the stability of the nucleus is the ratio of protons to neutrons, okay? So here is a graph that shows number of neutrons on this axis and number of protons on this axis, okay? So as you go from 0 to 100, you know, these are the different atomic numbers of the elements, right? So carbon, you know, carbon is atomic number 6, so it's down here somewhere and so on. These little dots are the stable nuclei, okay? The nuclei that don't have any radioactive decay, all right? And you notice a trend, right? The yellow dots are nuclei that radioactively decay, all right? But notice this trend. For light elements, like for example, carbon has 6 neutrons and 6 protons, right? Carbon 12, that's the most abundant element of carbon. There's also some carbon-13, but this is the most abundant one. So we see that its ratio of neutrons to protons is 1, right? One neutron to every proton. For lighter elements, that's generally the case, as you can see here, right? This red line is N to Z equals 1. That means you have 1 proton to 1 neutron. So for lighter elements, it's going to be about 1 to 1, all right? Once you get to heavier elements, once you get above 20, then the stability requires more and more neutrons compared to protons, right, to have a stable nucleus. So when you get from 20 to, let's say, about 40, that ratio is about 1.25. And for heavier elements, it approaches 1.5, right? So here you see, for example, zirconium, right, 40 to 9, it has 40 protons, 50 neutrons. The ratio is about 1.25. And here for real heavy elements like mercury, right, the stable nuclei have, in this case, 120 neutrons to every proton for a ratio of 1.5, okay? 120 to 80, sorry, for a ratio of 1.5. So does that make sense? So given that, oh, I see a couple questions. Louis, go ahead.
Is that correct on the slides? It says 1 to -20 and 20 to -40, or is that just supposed to be?
Oh, that shouldn't be negative. That should just be to 20. There's okay. There's no negative. Sorry about that. Yeah, I don't know. Right. You know what? I think those dashes are just an artifact of the arrow or something like that.
Got it. Thank you.
Yeah, good question. Sorry about that. Taylor?
My question was on, so it says approaches. So if we got like a number that's over 1.25, then it would be unstable?
Correct.
Or, okay.
Right. So for example, let's say you have an element that is in, let's say it's in this region. So for example, suppose you have an isotope of zirconium that instead of having a mass number of 90 has a mass number, let's say, of 100, right? So then you know that that zirconium has too many neutrons to be stable, right? So if it has too many neutrons to be stable, what kind of decay gets rid of a neutron and turns it into a proton?
Beta decay.
Beta minus, right? Beta minus gets rid of a neutron and turns it into a proton, right? So if you're above that ratio, in other words, if you look at these little like line, these dots here, these blue dots, if you're above those dots, in other words, if the ratio is above those dots, then you're going to undergo beta minus decay, right? So up here, any isotopes that are up here, like in the yellow above these dots, are going to undergo beta minus decay. Now, what happens if you're below that line? Then what do you have? You have too many protons, right? So if you have too many protons, what's going to happen? What kind of decay will get rid of a proton and give you a neutron?
Positron decay.
Positron decay,
Or
right? Or
addition.
electron capture, right? Or electron capture. Okay, so let's just see if we can use this to make some predictions. So let's take antimony 132. Okay, here's antimony 132. Now, one way you can see where the stable nuclei are is you can look at this curve. You can look at this graph, right? And you could say, oh, okay, antimony is 51. For 51, should go up. Okay, the stable nuclei should have about what, maybe 70 neutrons, right? So the stable mass number should be about 120 or so, right? This is 132, so it has what? Too many neutrons, right? It has too many neutrons. So since it has too many neutrons, what kind of decay will SB132 undergo?
Beta.
Beta minus, right? So SB132, SB132, 51, you'd predict beta, right? You'd predict beta decay so that one of those neutrons will change into a proton, and maybe several beta decays, right? Now, there's also a shortcut to this. You don't have to look at this graph every time because the molar mass of an element is based on the stable nuclei, right? So notice what we did. We went to this graph and we said, aha, for 50, right, you should have about 70 neutrons, so you should have about 120 total mass number. Well, look at what the molar mass of antimony of SB is, 121, right? Why is it 121? Because the stable nuclei, right, have that mass number, right? So another way to figure out where the stable nuclei are is just to look at the periodic table, right? So instead of looking at this graph, we could look at the periodic table and said, aha, the stable nuclei lie about 121. This isotope is 132. I can tell it has too many neutrons, right? And therefore it'll undergo beta minus decay. Does that make sense? All right, how about phosphorus 27? Well, now let's just use the periodic table instead of using that other graph. So here's phosphorus. We see that the stable nuclei have an atomic mass of about 31. So is this nucleus too heavy or too light?
Too light.
Too light.
Too light, right? It doesn't have enough neutrons, right? So what you want to do here is you want to convert a proton to a neutron. How do you do that?
Positron emission.
Positron emission, right? So phosphorus 27 is beta plus positron emission, okay? All right, one more here. How about barium 123? So again, we'll look here at barium. Barium is atomic number 56. Its atomic weight is 137. So does this have too many neutrons or too few neutrons for barium, for this isotope?
Too few.
Too few, right? So what would we predict for barium 123?
Positron.
Again,
Yeah, positive.
positron. By the way, whenever you do positron, it could also be electron capture, right? Or electron capture or electron capture. Does that make sense to everyone? Okay, how about you try this one? And I will, I'll put up a poll here. And it's hafnium 151. Hafnium 151 is right, where is hafnium? Right here. All right, a few more seconds, try to put in an answer here. Okay, very good. So the right answer was B, and most of you got that. So nice work. And the way you would do that is, again, you go to hafnium 151, which is here, right? You'd see that the stable isotopes have a mass of about 178, right? This has a mass of 151. So not enough neutrons, right? Not enough neutrons. So if there's not enough neutron, it's going to be positron emission. Okay. Does that make sense? Any questions? All right. Very good. Now, we've sort of looked at each of these decays as if they were isolated events. That, in fact, is not the case. Oftentimes, an unstable nuclei will undergo several different steps in order to finally get to stability. All right. So, for example, here's uranium-238. We saw that it undergoes an alpha decay. An alpha decay, of course, this graph here is doing number of protons, number of neutrons, right? So if uranium-238 loses an alpha particle, right, it loses 2 protons and 2 neutrons, so it becomes thorium-234, right? But then thorium-234 itself is not stable, okay? And thorium-234, 90, actually undergoes a beta decay. To become palladium-234. So this equation represents this step, right? To go from here to here. Okay, and then that'll undergo another beta decay to become uranium-234. And then uranium-234 undergoes 1, 2, 3, 4 alpha decays in a row, right? And you see how this uranium is slowly losing weight and getting smaller and smaller. Because remember what we said, all elements above bismuth are unstable, right? And then it continues to decay, and then there's some options here. It can either go this path or this path, but eventually look what happens. It goes down, 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 and it eventually becomes lead. Okay, so all uranium-238 is radioactively decaying through this chain of events to eventually become lead, right? And the lead, of course, if you look at the periodic table, right, here's lead. Lead has stable isotopes. Okay, remember the heaviest element that has stable isotopes is bismuth. Every element above bismuth, no stable isotopes, are all radioactively decaying to something else. Now you might ask, well, why do we have these heavier elements, right? Well, because they tend to have long half-lives. In other words, it takes a while for the process to happen. And we'll talk about the kinetics of radioactive decay here in just a minute. All right. A couple of quick questions. Taylor.
Can you go to the graph that you had for the, yeah, that one. I don't know if it's just me, but this graph looks similar to the other graph, the
Yeah.
decay. When was it? No, there we go. That one. Does it follow this path because it falls in that ratio?
It's
Is
basically going from like where what let's see, what was it? It was uranium-238, right? So 230, so uranium is 92, so 238, right, is up here, 192. So it's like starts out up here somewhere, right? And it's basically just going chick, 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 coming down to here.
Okay,
It's
so it
trying to
stays in
keep-
that yellow area.
It stays in the yellow area, and it's
Okay.
getting to one of these stable isotopes, which are the little green dots.
Because it looks like it could just do a bunch of alpha decay and then like a few beta decays to get there, but it wouldn't do that because
Yeah.
it would be outside the yellow area.
Again, the exact details of the order and all of that is kind of hard to predict from what we know, but we can predict two things about this. One is that it's going to be a heavy one, so it's going to lose weight, and eventually it's going to have to get the ratio of protons to neutrons right, and so that's why it's undergoing these betas.
Okay, so it's going to follow some pattern to keep the ratio
Correct.
like
Yeah.
within. Okay, I was just curious, like his
Yeah, to
concept
try to get
question.
to a stable ratio. Yeah.
Okay, thank you.
Rylan.
Do all elements that are all heavy elements necessarily decay to lead then, if they're all shooting down to gain stability?
They can decay to, well, at least to lead, right? So bismuth is also a possibility. They can decay to bismuth. They can decay to lead. They tend to decay to these elements here, right?
Okay.
Bismuth. I think mostly bismuth, lead, and maybe tellurium.
Got it.
Good question though. I don't know the exact breakup of where they end up, but yeah, they end up in these in this area for sure. Okay, very good. All right, let's have a quick look at the kinetics of radioactive decay. So we learned about chemical kinetics already, so you've already seen the equations that govern this. The nice thing about radioactive decay is that it's all first order. So do you remember from not last semester, earlier this semester, when we looked at first order kinetics, right? Remember that rate, we had the rate equation, right, which said that rate is equal to K times the concentration of A to the N, right? And N could be 0, 1, 2, right? 0 order, first order, second order were the most common ones, right? So for radioactive decay, this is chemical kinetics that we already covered, right? For radioactive decay, N is equal to 1, right? It's first order. And usually instead of concentration, we write N, where N is proportional to the number of radioactive nuclei. So the equation becomes rate is equal to K N right? That's the rate equation, right? First order. Okay. So this is the rate law. It follows first order kinetics, right? So if we look at, let's say we have a sample that's radioactive, right? And it's undergoing radioactive decay. And initially we have 100% of that is that radioactive sample, whatever it might be. It might be uranium-238. It might be one of these other things we've been looking at. It doesn't matter, right? But what's going to happen is over time, it's going to decay away, right? The number of radioactive nuclei is going to decay down, 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 and it's going to follow a first order decay kinetics, right? If you remember from first order kinetics, the half-life was a very convenient number to use, especially for first order. Why? Because for first order kinetics, the half-life is independent of the initial concentration, right? So every time a half-life passes, the concentration falls to 1/2 of what it was before, right? After 2 half-lives, you get 1/4 of what you had before, right? For radioactivity, if you have 100% of your sample, right? After 1 half-life, it falls to what? 50% of what you had, right? After 2 half-lives, it falls down to 25% of what you had, right? 693. And so on. And so you see over time, right, it decays away. That means that, and of course, that means that the parent nuclides become the daughter nuclides, right? So if you were to plot the daughter nuclides, right, they would go up in concentration, right? But we're just going to focus here on the parent, and we see that it decays away in the first order fashion, right? So here is a gas called radon-220. Radon-220 is, let's see. Well, here's radon-222. Where's I guess radon-220 is not on here, but radon-220 is a process that is a gas that's being given off by some of these radioactive decay processes. All right. So it has a half-life of 1 minute. All right. And so that means if we start out with 1 million atoms of radon-220, right, after 1 minute, we'll have 500,000, right? And after 2 minutes, we'll have 250,000, and then 125,000, and so on, right? And it'll fall to half of its initial value with each half-life. Okay. Now, the half-lives for radioactive elements is all over the map. All right. Sometimes you have very, very long half-lives. So for example, uranium-238 we saw as an alpha emitter, right? It undergoes alpha decay, and it has a half-life of 4.5 billion years, right? So very, very long half-life, okay? On the other hand, some things like thorium-219 here has a half-life, and it's in only 10⁻⁶ seconds, right? A microsecond. So it decays very, very quickly, all right? Carbon-14 here is another one I want to call your attention to. It has a half-life of 5,715 years. All right, and we're gonna see how we can use some of these elements are used as clocks to measure time. Okay, and so we'll look at that in just a minute. Okay. So the first one we'll look at here is radiocarbon dating. And if you have, in the atmosphere, you have some carbon-14. And the reason you have carbon-14 in the atmosphere is because, 4/5 of the atmosphere is nitrogen. And when nitrogen gets bombarded by neutrons that come in from outer space and from other stars and into our atmosphere, it hits the nitrogen, collides with it, and that forms carbon 14-6 and 1 hydrogen atom. Okay, so this process is always occurring in our upper atmosphere. So in our upper atmosphere, we're constantly forming carbon-14. All right, and then carbon-14, though, however, is unstable, right? and it undergoes beta decay. So it undergoes beta decay like this, right? And that forms nitrogen 7, 14, all right? So it basically just goes back, right? The nitrogen turns into carbon 14, but then this goes back, and this goes back with a half-life of 5,715 years, okay? So why is that important? Well, since there's a certain amount of carbon 14 in the atmosphere, right? There's a certain amount of carbon 14 in all living things, right? Because the carbon that is, for example, in our body, right, comes from plants that we eat or animals that we eat, right? And those animals ate plants, right? And those plants were all undergoing photosynthesis, right? So they were taking carbon dioxide from the atmosphere and making sugars and proteins and everything else, right? So basically the amount of carbon 14 in the atmosphere right now is identical to the amount of carbon 14 in our bodies or in the body of any living thing, right? So any living thing has some equilibrium amount of carbon 14. Now, what happens when the organism dies? That carbon 14 begins to decay, right? So initially, it has the percent carbon 14 relative to other living organisms is 100%. All living organisms have the same amount of carbon 14, right? Relative to all their carbon, which is what we measure, right? And so the percent carbon 14 relative to other living organisms is 100% while it's alive. Then the organism dies, and what happens? In 5,715 years, right, it has a carbon 14 that's 50% of what living organisms have, right? And in 11,430 years, it has a carbon 14 that's 25% of what other living organisms have, right? So if you find an ancient skull or an ancient bone or some ancient thing that was once alive, you can measure its carbon 14 content, right? And that tells you how old it is, okay? So for example, these are a picture, this is a picture of these scrolls called the Dead Sea Scrolls. They were discovered about 50 years ago, 60 years ago, actually 70 years ago now. They are biblical manuscripts, so manuscripts of the Hebrew Bible, okay? And these were written on papyrus, which was once living, right? So we could examine that papyrus and tell how old it is, right? How do we do that? We take a small amount of it. We measure how much carbon 14 is in there, right? And we can compare that to what it is for living organisms, right? And what we found in that case is that it was about 70 or 80%, which gave a time of about 2,000 years, right? So you can figure out that these scrolls were 2,000 years old, right? So you can tell that they were genuine and not some fake. It wasn't something that someone put in the ground 100 years ago, right? They're the real deal. And you can tell that because the carbon 14 in them is a signature of how old they are. Yeah, it looks like age-line notebook paper. Yeah, absolutely. So the carbon 14 is measured by, you take a sample, you weigh it, you determine how much carbon is in that sample, and then you basically measure the number of beta decays that you have per unit time, right? And that'll tell you how much carbon 14 you have, right? Because the rate is proportional to the number of carbon 14 atoms, right? So that's how you do it. And then you just look at that relative to the living things, right? And then you can tell the age. We'll do an example. We'll do an example here in a minute. Now, one thing that they noticed when they were developing this technique is that in some cases, the measurements could be off by a few percent. And how did they know that? Well, you can measure the age of something using carbon 14. And then if that particular document or that particular thing, artifact, had some sort of way to measure its age from history, right? From what we knew about history, like for example, let's say we knew it was, part of it was a result of the reign of some king or queen, right, that we knew the dates of, right? Then you can measure the date two ways, right? You can measure it historically from what you know from history, and you can measure it from carbon-14 dating. And again, the carbon-14 dating was always usually pretty close, but sometimes it could be off by a little bit. Why is it off by a little bit? Well, it turns out that this reaction, right, can differ a little bit over history because of the amount of neutrons coming into our atmosphere, which can differ a little bit over history, right? So in other words, the amount of carbon-14 in the atmosphere can go up and down by a few percent, right? But what we can do is we can calibrate for that. We can correct for that. And this is so cool. How do we do that? Well, there are these very old pine trees called ancient bristlecone pines. And if you ever drive up to Mammoth along the 395, you can go see these trees, all right? They're off the 395. You drive towards Death Valley, and you can go to what's called the ancient bristlecone pine forest, right? And you can see these trees that are about 5,000 to 6,000 years old, right? If you can believe that. So these trees in their trunks, right, contain a record of how much carbon-14 was in the atmosphere on that year. So for example, you can count back 300 years by counting back 300 rings, right? You could take a sample of that wood, right? You can account for how much has decayed due to carbon-14 decaying, and then you can figure out, okay, how much carbon-14 was in the atmosphere that year 300 years ago, right? Isn't that crazy, right? You can actually do that. And so what that does is you can correct the carbon-14 measurements so that instead of being off by 5%, they're only, they're accurate to within better than 1%, right? So that's basically a way of calibrating carbon-14 dating. And not only that, there are also dead trees that have been recovered from this area, all right? And some of those dead trees have been dead for 5,000 years, all right? But because there's some overlap in the lives of those trees and the lives of living trees, you can actually use the rings from those dead trees to calibrate this back even further to about 10,000 years, right? Oh, is that right, Ryland? SBCC will take you to see the trees. Have you been there?
Yeah, Matt K, killer class.
Oh, awesome. So you went and saw these?
Yeah, it was really cool.
That's
I
amazing.
got a whole journal full of drawings of them.
Nice, nice. Yeah. So pretty cool, right? We can use these trees and we can now get carbon dating to be accurate within 1% for actually up to about 11,000 years ago. Beyond that, it's believed to be accurate about 5%, up to about 50 or 60,000 years. So carbon-14 dating can be used to measure the ages of things up to about 50 or 60,000 years. The last 11,000 years within 1%. Beyond that, about 5% accurate. Yes, yeah, for those 11,000 years, that's kind of the gold standard because you can use this to calibrate the measurements. All right, let's see how this works. So typically what you can do is you can measure, because the rate is proportional to n, right? What you can do is you can say that, and if you remember the first order rate law, right? The log of nt over n0 is equal to minus kt, right? That's the first order integrated rate law. When we saw it last time, we had concentrations in here, right? When we were looking at chemical reactions, but for nuclear decay, we use n, right? So the log of the number of nuclei at time t divided by the log at time 0 is equal to minus k, that's the constant, times time, okay? Think about this equation that we saw before. Right, this is the one we saw for chemical kinetics. This is the equivalent equation for radioactive decay, all right? Now, one other thing to realize here is that rate, since this process is first order, rate is directly proportional to n, right? So instead of putting n here, you can also put rate here. So we could put log of rate of t over rate at time 0 is equal to minus kt. All right, and this is typically what we use for carbon-14 dating. Okay. So let's look at this example. There's an artifact, an ancient bone, has a carbon-14 decay rate of 0.48 disintegrations per minute per gram carbon. Okay, those are just the units they use, right? Disintegrations is number of decay events per minute per gram carbon, because you gotta, of course, normalize for how much carbon you're weighing, right? How much carbon you're analyzing. And so it says that that's the decay rate this bone has, right? Living things have a decay of 15.3 disintegrations per minute per gram carbon. All right. So in other words, this is rate at time 0, right? When the organism died, this was its disintegration rate. And this is its rate now. Right? That's a good question. You could do it in moles if you want as well, Taylor. That's just the way they typically do it. I'm not sure why. So then if you want to figure out, okay, how old is the bone, then you just got to look at this equation, right? Natural log of rate at time t over rate at 0 is equal to minus kt, right? You know the rate at time 0, right? You know the rate at time t. You're trying to solve for t, you need k, right? How do you get k? From the half-life, because t 1/2 is equal to 0.693 over k. Over k, right? So k is equal to 0.693 over the half-life, right? Which is equal to 0.693. The half-life is 5,715 years, right? So that comes out to be equal to 1.21 times 10 to the minus 4 per year. Okay, that's the rate constant k. So that's what we're going to plug into that. And we're going to solve this for t, right? So t is going to be equal to what? Minus 1 over k times the natural log of the rate at time 0 the rate at t divided by the rate at 0. Okay, so that's equal to minus 1 over 1.21 times 10 to the minus 4 per year, right? Times the natural log of rate at time t. We're given that as 0.48. And the rate now, the rate at time 0, which was equal to 15.3, right? And we plug all that in and we get 2.9 times 10 to the 4th years, which is about 29,000 years, right? So that bone is about 29,000 years old, right? So that's how we can measure the rates of these ancient artifacts that have been discovered, right? As long as they were once alive, they had the amount of carbon-14 that living organisms have now, give or take 5%, right? And then that decays away with a half-life of 5,715 years, right? So for example, just to get this idea in your head, right? If the rate now is half of what it was then that thing is 5,715 years old, right? But no matter what that ratio is, you can always plug it into this equation and you can solve exactly for how old that artifact is. Does that make sense? Oh, thank you. Diss. That's when you put someone down, right? You diss them. Is that what that is? Sorry. disintegrations. Disintegration. Or a decay, right? A decay event. Bad attempt at a joke. Sorry. Let's see. What else? Any other questions? Okay, here's a quick question for you. Go ahead and try this. All right, go ahead and try to answer that question in the next few seconds. I'm going to end the poll here. Okay, very good. The right answer was A, and virtually you all got that. So nice work. How do you tell? Notice the half-life is the time it takes to get to half of its initial concentration, right? So if you look, it had 1 million atoms, and then it fell to 500,000. How long did that take? 1 minute, right? So that tells you the half-life is 1 minute. Notice that in another minute past that, it goes from 500,000 to 250,000, right? And it falls in half again. And it just keeps doing that every minute, right? That's the definition of half-life. All right. Okay, what else can we measure this way? So we can measure the ages of artifacts this way. This is also the way we get an estimate for the age of the Earth. All right. So we saw that uranium-238, right? You saw that decay series earlier, right? That it decays through a number of steps and ends up as lead-206. All right. The half-life for this process is 4.5 billion years. 4.5 times 10 to the 9 years. All right. So what that means is that whenever we find lead-238 on Earth, guess what else we find with it? What do you think? If it's decaying to lead-206, right? Whenever you find uranium-238, what else do you find with it?
Lead.
On lead.
Right, lead-206, right? And the ratio between uranium-238 and lead-206 is going to tell you when that uranium was originally formed, right? So uranium was formed originally, of course, in fusion and fission reactions that happened during star formation, when a star dies, right? And then when the planets form, that uranium crystallizes, right? And it'll form basically solid uranium, okay? And then that solid uranium is then gonna decay with a half-life of 4.5 billion years, okay? So what you can do then is you can find these rocks that contain uranium and then measure the amount of uranium to lead. So what we found on Earth is that on every continent, we have ratios of rocks with lead to uranium that are about 3.5 billion years old. We found rocks that are that old based on this dating technique, okay? The very oldest one, so on every continent, the very oldest ones that have been discovered on Earth are about 4 billion years old. And then we've also been able to look at the uranium to lead ratio in meteorites that have landed on the Earth. And those, we found about 70 that have an age of about, so these are the oldest. And then these are what we found from meteorites, right? So, you know, the Earth was formed some 4 to 4.5 billion years ago, all right? So that's about, usually they put the age of the Earth or the age of the solar system at about 4.5 billion years, okay? By the way, the universe is about 13.7 billion years old. All right, and that's measured using different kinds of techniques. You can't measure the age of the universe from lead uranium because obviously the universe is a lot bigger than what we can access, right? But the way they measure the age of the universe is based on how fast stars are moving away from us and from each other. And you can measure that because the light is shifted due to the Doppler effect. Right? So you can imagine, have you ever seen when you have a train coming towards you and then after it moves away from you, the pitch changes, right? The pitch is usually higher as the train is coming at you. And then the pitch goes lower as the train is moving away from you, right? So as stars move away from each other, when we look at stars, as they move away from us, they get the light that we see from those stars gets redshifted. And we know what wavelengths those should be because they correspond to certain elements. Like for example, hydrogen in a star will give off light of certain wavelengths. When we observe that light from the Earth, we see that it's shifted from the wavelength that it should be. Why? Because the star is moving away from us. So we can figure out how fast the star is moving away from us. And then you can basically back all that up and figure out when the Big Bang happened, right? When the original Big Bang formed the universe. And when you do that, you get a number about this old. So that's why, you know, we think that the sun, right, is about a second or third generation star, right? And of course, it has to be that way because in order to have planets, right, stars just have hydrogen and helium basically. And it's only when a star dies that it can form the heavier elements that then form planets like Earth, right? So it's kind of nice because it kind of coincides with what we know in terms of star formation and how the universe is. Okay. Let's see. Questions? Any questions? Taylor.
So,
Never mind. Go ahead, Xavier. Hold on. Or was I first? Wait.
Well, you had your hand up first, so go ahead, Taylor, and then I'll call on Sophia next.
Okay. So if our sun is a third or second generation star,
Yeah.
the first generation, did that make uranium that's on our planet that's on Earth, or?
Yeah, the
Okay.
generation before ours, right? Exactly correct. So when a star, all the first stars that in the first generation stars of the universe, right, all contained only hydrogen, and basically stars through a process which we'll look at in just a few, probably not today, but next time. Well, maybe we'll get to it. Basically take hydrogen and form helium through fusion. And that gives off a bunch of energy, right? And so that's how stars burn, and they burn for, I don't know, several billion years, right? And then they eventually burn out. And as they burn out is when you get all these other events happening of fusion and fission, which end up creating the heavier elements.
Yeah.
So it's the death of a star that creates. Now, and then if a new star is born in the region where an old star died, right, as I understand it, I'm not a cosmologist, so this is just like the super simplified version. if another star forms in the vicinity where another star died, then it can form, planets can form around that star, and those planets come from the heavier elements that were formed from the death of the previous star.
Yeah. Okay.
Does that make
Yeah,
sense?
I heard it. I heard the sun can, or fusion can go until it hits iron, I think it was, and then
Yes.
it can't get energy out of it.
Correct. So then you got to put energy in to get above iron, and we're going to look at why that is as well in a few minutes. Not in a few minutes, probably next time.
Okay. All right.
Yeah. So the fusion of everything to iron gives off energy, right? So the fusion of anything beyond iron actually takes energy. But if you have enough energy around from fusion, you can create those heavier elements as well by putting energy in. They're endothermic, but they happen.
So is that why they're rare, or rarer, I should say? Or like there's less of them? Or
I don't. Good question.
because it like
I'll
the sun
venture
would
to guess.
die, right?
I would guess yes, but I'm not 100% sure.
Okay, I'll have to look that up. That's interesting.
Yeah, it is super interesting.
Thank you.
Every element after uranium is man-made or human-made. There were some women involved, so that's good. Let's see. I saw a bunch of questions here. If you come across lead, is it possible uranium is still in the area? There's uranium everywhere. So there's uranium probably in the ground beneath you right now, and it's decaying, and it's giving off alpha radiation and beta radiation and everything else. So we have evolved in a world that has radioactivity, right? Small amounts of radioactivity are normal and not very dangerous. Large amounts of radioactivity are rare and very dangerous. So we'll talk about that too, about how radioactivity affects living organisms. Basically, what happens is that if you think about these energetic particles being given off by nuclei, right? When they interact with other atoms, they can ionize them, right? They can kick off electrons, all right? Because they have all this energy, they can come in, boom, kick off electrons. When they interact with molecules, they can do the same thing. So normally, when they interact with molecules, it doesn't really matter. The molecule gets ionized and whatever, it goes on to react. But when it interacts with living things, it can ionize molecules within cells. Now, most of the time, that's not a problem either. But if the radiation interacts with molecules in the nucleus of the cell, and especially DNA, right, it can alter the DNA of a cell. And again, most of the time when that happens, the cell just dies, right? Because it doesn't have the right directions for the cell to multiply and grow, right? However, occasionally, once in a billion events or something like that, it can ionize the DNA in a cell so that the cell begins to multiply abnormally, right? And that abnormal multiplication can be cancerous, for example. So exposure to too much radiation can increase your risk of cancer. Right. And so again, we'll look at that more a little bit later, but that's why radiation is dangerous, and you don't really want to be around a lot of radiation. But again, we're exposed to radiation all the time. It's all around us, small amounts, not a big deal. It's the larger amounts, and the real larger amounts you got to be worried about are not the uranium that's in the earth so much, but rather the amount of radiation that would be next to, let's say, a nuclear bomb, right, that went off, or at the core of a nuclear reactor, right? Those amounts of radiation are dangerous and can really increase your risk of bad outcomes. Okay, what else here? Yes, every element after uranium is man-made. All right, good. Cool stuff. All right, Sophia. Sophia, did you have a question?
Yeah, you were saying that the universe is 13.7 billion years old.
Yeah.
And the first meteorites, are those first generation stars, like they come from, or is it also?
So those meteorites that are about 4.5 billion years old are in our solar system, right?
Okay.
They were formed when our solar system was formed. So they're a good measure of how old our solar system is, right? So our solar system seems to have been formed about 4.5 billion years ago.
Okay. All right. Thank you.
Does that make sense? They're basically meteorites that are orbiting the sun, right? There's certain meteorite belts, and there's meteors, you know, that come in. So these are the ones that are in our solar system. Good question. Any other questions? All right, good, good. All right, let's see, a couple more minutes. Let me introduce the idea of fission, and then I think we'll end with that. Let's see, in the mid 1930s. So I want to transition over here to fission, and the story there begins in the mid 1930s. And there was a scientist, Italian scientist by the name of Enrico Fermi. And at the time, no one, you know, the heaviest known element was uranium. Okay, if you look at our periodic table, it has a bunch of elements beyond uranium. Those are all synthetic elements, right, that we have created in labs. But at the time, uranium was the heaviest known element. So Fermi wanted to try to make elements heavier than uranium. And people were starting to understand some of these nuclear processes, right? So Fermi had this idea that he's going to take uranium-232 and bombard it with a neutron, right? And that would make uranium-239-92. And he figured that that would be unstable, right? More unstable than, of course, uranium-238 is itself unstable, but it has a very long half-life, right? So this would be even more unstable. And he thought that this would then give off a beta particle, right? And it would therefore form an element with atomic number 93. And let's just call that element X, because at the time it wasn't known, right? So Fermi thought, oh, wow, I can synthesize elements that didn't currently exist, right? So he tried the experiment in the mid 1930s. He did this, and the way he tested for what was happening was he looked for beta particles, because beta particles are fairly easy to detect, right? So he looked for beta particles after he bombarded the uranium with neutrons. And sure enough, he detected them. And he thought, I've made a heavier element, right? Now, Fermi was a physicist, unfortunately, and he didn't really understand too much chemistry. So luckily, the chemists came to the rescue. And in 1939, 3 chemists in particular, Liz Meitner, Otto Hahn, and Fritz Strassmann. How do you spell Strassmann? What they did is they said, okay, they did the same experiment. They detected the same beta particles, but then they chemically examined what else was there, because of course they were interested in the chemistry of this new element, right? What were its properties, right? What did it do? So when they looked for this new element, they didn't find it, okay? What they found instead was some lighter elements. They found barium and krypton. And that was weird, right? That was weird for a couple of reasons. One was that every nuclear process that had been discovered to date had always resulted in small changes in the nucleus, right? So maybe a uranium atom loses a couple of protons and a couple of neutrons, or maybe a proton turns into a neutron, right? But there hadn't been any processes like this, which were radical changes, right? Here you have a big atom and you basically split the atom into 2 smaller ones, right? That was revolutionary. And that is called nuclear fission. Split large atom into 2 smaller ones. All right. So basically, these 3 scientists, who were working in Germany, discovered this process. All right. And not only was this process happening, but it was emitting a large amount of energy. And the amount of energy that it was emitting was far greater than any known chemical process. All right. So, and about 1 million times more per gram, if you can imagine that, right? So, yeah, they didn't blow themselves up because they were, this was only happening on a very small scale, right? So we only had a few, a very small number of atoms sort of undergoing this process. In order to get this to produce a lot of energy, there was still more work to be done. You had to create basically a nuclear bomb, which they which we eventually did. But this was a huge discovery. And at the time, people realized, oh my goodness, this could end up making a bomb that is very, very powerful, right? Because here's what's going to happen. Notice that the products of this reaction are also the things that are needed for the reaction to initiate, right? So the products are 3 neutrons. So 1 uranium nucleus, when it undergoes fission, produces 3 neutrons. So those 3 neutrons can then induce fission in 3 other uranium atoms, right? So 1 uranium atom undergoes fission, it creates 3 neutrons, it can induce fission in 3 others. Each of these then produces 3 neutrons, which can induce fission in 3 others and 3 others and 3 others, right? And so what do you have? You have basically a self-amplifying chain reaction, right? And people realized quickly that this could be used to make a nuclear weapon, a bomb, right? And so at the time, what a few scientists did is they convinced Albert Einstein to write a letter to the US president and warn him about this, right? What was going on in Germany, that the Germans had discovered a way to perhaps build a very powerful bomb. So here's what Einstein wrote to FDR. This new phenomenon would also lead to the construction of bombs, and it's conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by a boat and exploded in a port might very well destroy the whole port together with some of the surrounding territory. However, some such bombs might very well prove to be too heavy for transportation by air, right? So that's what Einstein wrote to FDR. And of course, it was wartime. So what did FDR do? He set into motion really one of the first big science endeavors of all time. Does anybody know what it was called?
Manhattan Project.
Correct. The Manhattan Project, right? And the goal of the Manhattan Project was to build the first nuclear bomb, okay? And it was sort of seen as this race against Germany to see who could build it first, right? So there was a lot of pressure. The central headquarters of the Manhattan Project was in Los Alamos, New Mexico, right? And a bunch of physicists and scientists were recruited to work on this project. Eventually, it was successful. In 1945, the first atomic bomb was detonated, and it had the power of 18,000 tons of dynamite, right? So 18 kiloton bomb. To put this in perspective, the modern bombs are 1,000 times more powerful than this. So this is 18 kilotons. Modern atomic weapons, which use fusion instead of fission, are measured not in kilotons, but in megatons, if you can imagine. So it would be 1,000, it would be the equivalent of more than 1,000 of these. And this was already pretty powerful. Now, by that time, what had happened? Germany had surrendered, right? And the bombs were then used on were dropped on Hiroshima and Nagasaki, right? During the end of World War II. And together they killed 200,000 people, unfortunately. Sort of a tragedy, but just shows you the power of these bombs. 2 bombs were able to kill 200,000 people. And like I said, today's weapons are measured in megatons, which is like 1,000 of these. So you can only imagine. Now, I don't want you to think that, you know, an atomic bomb can destroy, you know, the world or something like that. But if a hydrogen bomb was dropped in downtown Santa Barbara, right? Most of downtown Santa Barbara would be wiped out. Carpinteria would still exist, but downtown Santa Barbara would mostly be wiped out, just to give you a sense of what these bombs are like. Let's see, Sophia, question.
Oh shoot, I forgot, sorry.
No problem. There's a lot that goes into creating this bomb, and you know, we don't really need to get into all the details of it, except you need to have what's called a critical mass. So you need to have a certain amount of uranium so that enough of the neutrons can bump into other uranium atoms to create the chain reaction. So that's one of the main things that is necessary to create an atomic bomb, is to have a critical mass. And you know, that was once top secret. Now you can look it up on the internet what the critical mass is, right? It's not a secret really anymore. But I think it's something like 30 kilograms or something like that. Can't remember exactly what it is, but it's in that ballpark, right? So you know, you need a good amount of uranium, but the amount of the energy concentration is huge, and that's what is so different about nuclear processes compared to chemical processes is the energy concentration. So this same process in a nuclear bomb, it's carried out in a chain reaction that's out of control, right? They intentionally designed to have a chain reaction that goes out of control. But you can carry out the same fission process in a controlled environment, and that is called a nuclear reactor, and that produces nuclear power, which basically just creates a lot of heat that you use to turn the turbine on a generator and create electricity, right? But just to give you a sense of how much energy is contained in this, let's say you had a nuclear powered car, all right? Now, of course, you can't have a nuclear powered car because the energy demands of a car are too small for nuclear power, right? But let's just suppose you could, and you didn't have to worry about critical mass or anything like that. And let's suppose you had, you know, a fuel rod that was the size of this pen right here, okay? Your nuclear powered car could run for 30 years under typical driving with this much fuel, right? That tells you how concentrated the energy is, right? You could run, so you would drive your car for 30 years and you wouldn't have to refuel it with just this much fuel. Compare that to how many tanks of gasoline you go through driving your car for 30 years, right? That gives you an idea for how concentrated the energy is in nuclear power, both in terms of a nuclear explosion, right? But also in terms of nuclear power. With just a small amount of fuel, you can generate a lot of electricity, okay? And so we're all out of time, unfortunately, so I'm gonna stop here, but that's where we'll pick up next time, looking at nuclear power and the generation of electricity through nuclear power. Sophia and Taylor, I see your hands up. I'll answer your questions as soon as I end class, okay? All right, well, thank you everyone. Thanks for your attention. I certainly appreciate it. Thanks for having your cameras on. You know how much I appreciate that. And I'm gonna end the class here. Have a great afternoon.